Hello, and welcome to today's webinar on compressed air. My name is Steve Koski. All of PGE's seminars and webinars are in part sponsored by the Energy Trust of Oregon. We work together to make sure the concepts and recommendations you learn in our events are consistent across all of our individual programs and services. To get us started, let's take a minute and mark the size of your compressed air systems and what type of compressors you have. Use the annotation tools on your left, click on the pen, and then pick a tool. You could use the pen tool or the pencil tool, or maybe you could draw a box around it. Mark your operating horsepower, and then kind of what type of compressors you have on the right. Yeah, the arrow works too, but then the arrow moves if you click something else. It's not persistent. Okay, so it looks like we have some mid-sized systems. Reciprocating compressors, some oil-free compressors. Nobody's got any oil-flooded screws yet so far. Nobody wants to speak up. All right. Well, that gives us an idea of what to speak to. Thank you. The goal of this training is to help you understand the advantages and disadvantages of using compressed air, to help you apply 10 energy-saving approaches and give examples of how they apply to compressed air, and help you find technical and financial assistance for energy-saving projects. Here's our basic path today, and like Beth said, I'm happy to answer any questions that pop up and follow rabbit trails, so don't hesitate to ask any question. In fact, the more questions you ask, the more this webinar will help you with your specific issues. Okay, first we're going to talk about how great compressed air is and also why it's terrible. Then we'll go through a generic list of ways to save energy on any system. Then we'll spend most of our time on 6 case studies where folks cleaned up their compressed air systems and saved energy. And at the end, we'll point you to some technical resources and answer questions. Compressed air can do about anything. It can push, pull, carry, cool, stir, dry, and disappear. It's easy. It's simple to connect. It won't shock you. It works in wet and corrosive locations. The actuators are low cost, light and small, and compressed air spills are self-cleaning. In fact, compressed air is so great that 7 of 10 industrial sites have compressed air, and 10% of the electricity in the United States goes to air compressors. At the same time, compressed air is also terrible. The problem is that air is very compressible, which means that when we compress it, a lot of the energy turns into heat. Let's do a little thought experiment here. Hold your hands out in front of yourself and grab about a gallon of air between your hands. Now, squish that gallon of air down to the size of a pint. So this would be an 8-to-1 compression and would give you about 100 psi. If you could do this and not let any heat escape, what temperature would that pint of air be? So use the text tool and type your guess somewhere on the screen. And after you type your guess, click somewhere else on the screen, and that will make your numbers appear to the rest of us. So the question is, how hot is this chunk of air going to be after we squish it from a gallon down to the size of a pint? I see 100 degrees, 200 degrees. Yeah, and we're going to use degrees Fahrenheit as our units. 100 degrees, 200 degrees. Astonishingly, our pint of air would be 500 degrees. Well, why Why aren't all of our compressed air pipes and tanks and hoses and everything melting down? Why aren't they all 500 degrees? Well, the heat of compression is thrown away in oil coolers, intercoolers, and aftercoolers. 85% of compressor power is turned into heat. So 100 horsepower makes 85 horsepower of heat and 15 horsepower of usable air power. So one way to think of an air compressor is that it's more like a fancy heater that makes compressed air as a byproduct. If we need 15 horsepower of power to the shop floor, we could spend $50,000 in air compressor power every year, or we could spend about $7,500 if we could do it directly with an electric motor. So what's the lesson? Compressed air is expensive, so let's use it carefully and let's make it efficiently. Now let's go through a generic list of energy-saving concepts that are relevant to about any system you can think of, whether it's lighting, irrigation, refrigeration, or anything else. Minimize loads. So one way we can save energy is to just reduce the demand on the system, which in our case means reducing the amount of compressed air that we need to produce. If it was refrigeration, it would mean reducing heat load. If it was pumping, we would reduce the total gallons that were required. Number two, use your best part load option. Most equipment is pretty efficient when it's operated at full capacity, but its efficiency can drop off radically when we only need 50% capacity or 10% capacity. And many times there are alternate ways to control a piece of equipment so that when it's at low capacity, the efficiency is still reasonably good. Number three, turn it off. This is self-explanatory. Let's get idle equipment shut down and isolated. Number four, minimize pressure drops. Sometimes there's a bad actor, and this might have a high pressure drop, which forces us to operate at higher pressure to compensate. This could be a plugged filter, undersized piping, or something like that. Optimize pressure settings. Well, we need enough air pressure to do the job, but excess pressure increases the compressor power and leak flow. Keep idling time to a minimum. This is related to turn it off. We can't instantly shut off most compressors, but we can set up the automatic controls to shut them off once they're no longer needed and allow them to restart automatically when they are needed. All right, technology. So from time to time, we see someone using the wrong technology for the job, and this can cause the system to be fundamentally inefficient and use more power than is necessary. Right size equipment. Now, undersized equipment won't get the job done, and plants are pretty good about buying more air compressors if the plant air pressure is chronically low. So undersized equipment isn't usually the problem, but occasionally we find systems that are much larger than needed and operating at low capacity where their efficiency might be very poor. Remove barriers to more efficient set points. I think that's self-explanatory. And make the most of your controls. Often systems already have controls in place that just aren't being used. Now let's look at 6 case studies that range from small to large systems. First, let's look at a small shop air system. This shop has 2 10-horsepower compressors, and they switch compressors each week. The operating compressor runs about 60% of the time. The air is used for pneumatic tools, some machining parts blow off, and an air-powered mixer for a 5-gallon bucket of bonding agent, and leaks, of course. The bonding agent has to be stirred constantly, so the compressed air system is kept on 24/7. Reciprocating compressors are typically 25 horsepower and smaller. They usually use start-stop controls, which is great because the less air you use, the less time they spend on. They have what we call perfect part load performance. So at 30% capacity, they use 30% energy. They also have a non-cycling refrigerated dryer. This type of dryer uses a constant amount of power regardless of how much air is being dried. This can be okay for small systems, but can end up as an energy penalty in large systems. Dryer manufacturers also make cycling refrigerated dryers, which basically match dryer power to the air demand so that at low air use, they don't use very much energy. A refrigerated dryer is probably what you're thinking. It has a small refrigeration system in it, just like a fridge or an air conditioner. It cools the air stream and strips out the condensed water. Then the air goes through a heat exchanger to warm it up before it goes out to the refrigerators and dryers. Refrigerated dryers are great for when the air users are indoors and when ultra-pure air isn't needed, as it might be for making medical products or electronics. And refrigerated dryers provide air that has a dew point of around 35 to 45 degrees Fahrenheit. If you need drier air than this, the next step up is a desiccant dryer, which typically produce air that has a minus 40 Fahrenheit dew point. And there are several kinds of desiccant dryers, and they're all more expensive to buy and to operate than a refrigerated dryer. So in general, refrigerated dryers are our friends, and we want to use them whenever possible. But the cost to operate this system, the electrical cost, was a little bit over $4,000 a year. So these guys pursued several upgrades. First, they went after several known leaks and repaired them. They also purchased an electric explosion-proof mixer for the bonding agent. Now, explosion-proof just means that if there's some fumes ignite inside the mixer motor, they can burn off without the mixer blowing apart. The previous air-powered mixer was inherently explosion-proof as it was just powered by compressed air, not electricity, so there's no risk of sparking. And getting the mixer off of compressed air allowed them to shut off the entire system on nights and weekends. And that took a little bit of training and follow-up, but in a short while, it just became second nature for the shift supervisor to shut off the compressed air at the end of every shift. This saved them more than half of their operating costs. You know, they went from over $4,000 to $1,500 per year for this project. So great savings for a small operation. Here's our list of generic energy saving concepts. Let's mark it up with the concepts that were used for this shop air system. You can use the pen or minimize loads, turn it off. I think those are two of the main ones. That's the only other one I can think of that really applies here is kind of the right technology. So by using that electric powered mixer, you know, that kind of allowed them to turn it off. So excellent. Here's another shop air system. These folks are running a 75 horsepower oil flooded screw compressor. This compressor can make 330 CFM of air, but it's averaging only 31% capacity. And it's in automatic mode, but the compressor doesn't unload. It operates in a modulation only mode, which we'll talk about shortly. They have a heated desiccant dryer, but you'll note that this dryer is sized for 550 CFM, which is quite a bit bigger than the compressor. There are no purge controls on the dryer. Their air users, their single biggest air user is the purge air for the dryer. Then pneumatic tools and shop air use, what they really want the air for. They also have a handful of timer drains to remove moisture from tanks and filters, and these actually totaled about 10% of their air use. But the system was pretty tight. They had very few leaks, and this was costing them $22,000 per year of electricity to operate. When we see mismatched, oversized, and misapplied equipment like this, it's often equipment that was purchased for pennies on the dollar. The problem is that the initial purchase price of equipment ends up being about 10% of the total cost of ownership over the life of the equipment. So getting a bargain on the wrong size or type of equipment can be a very expensive mistake. Back to inlet modulation control. This type of control adjusts the inlet valves, the compressor, so that the flow into the compressor matches the flow of compressed air that's being used. It's low cost and can produce a fairly steady discharge pressure, but it has terrible part load performance. At full load, inlet modulation can be just fine. You can see up here it's using 100% power, making 100% flow. But at 0% flow, a modulating compressor uses about 70% power, and linear in between. So at 50% flow, it's going to use about 85% power. So we're wasting a lot of power when at medium and low capacity. Now let's take a peek at the right half of the screen and discuss desiccant dryer regeneration. Desiccant dryers usually use some compressed air and perhaps some electric heat and maybe some blower air to regenerate the dryer. They're drying the desiccant out so that it can dry the air for us again on the next cycle. And many desiccant dryers have energy-saving controls to match the regeneration with the moisture load. If you don't have energy-saving controls or you have them bypassed, then the dryer constantly regenerates regardless of moisture load. Now, these moisture sensors are not bulletproof. They will fail at some point, and you'll have to bypass the energy-saving mode just to keep the dryer functioning until you service or replace the sensor. But most people just forget about it and leave the dryer in the constantly regenerating mode, and this makes the compressors work harder to produce more air. So you can see here, they've got the purge saver, but unfortunately they've got it turned towards off. Moisture load control has been flipped off. And this last one, it's gone from a kind of a demand-based mode to a fixed-based mode. Now this shop decided to essentially replace their compressed air system. They installed two 15-horsepower screw compressors that used load-unload control. They put in a 2,500-gallon tank, and they replaced all the timer drains with no air loss drains. They put in a refrigerated dryer, and this was about a $55,000 project. Now, they could have cleaned up the operation of their existing equipment. They could have used the load-unload controls on their existing compressor and added purge-saving controls to the dryer. But this equipment was so badly sized that they just decided to start over. Now, why such a big tank? Our normal tank sizing rules of thumb would tell us about a 300-gallon tank would be fine for load-unload control on 15-horse compressors. Well, the super large 2,500-gallon tank allows enough air to be stored so that the compressors can shut down on every cycle. If the storage is smaller, they'll unload, but they won't be able to shut down. Now notice that they got away from the desiccant dryer and moved to the refrigerated dryer. They decided all their air use was inside the heated shop that didn't get below 50 degrees, and they didn't need super low dew point air. They did install some heat trace and insulation on the tank drain, as the tank was so large it had to be installed outside on a compressor, on a pad, on a cement pad, and they had to keep that drain line from freezing. Why did they install two 15 horsepower compressors? Well, they rarely need the second compressor. It's off over 90% of the time. And with several smaller compressors, you can stage up and down very efficiently to match the load, where if you only had a single large compressor, you could be stuck with some big inefficiencies when you're operating at medium or low loads. And you can see this is about $15,000 per year savings. So they were wasting a fair amount of money with their oversized and mismatched equipment. So let's mark this slide up again on which strategies this shop used to save energy. Yeah, right technology. They got rid of that desiccant dryer, got on the refrigerated dryer. That was their biggest load, was the dryer purge, so minimizing loads for sure. You use your best part load option. Yep, well, there you got. They moved to load unload control instead of inlet modulation, and keep idling time to a minimum. Yeah, the big tank did that. The right size equipment for sure. You know, 75 horsepower was way more air than they needed. So thank you, that's very good. Now let's move to just back a little smaller system. This is a system that's dedicated to a palletizing operation. They had a 30 horsepower oil flooded compressor, and this compressor has this handoff auto switch, but no one there had ever seen it in anything but hand. They didn't even know what auto did, so it was always operated in hand, which kept it in the inlet modulation mode, wouldn't let the compressor unload. It had a heatless desiccant dryer. They were running 125 to 130 pounds of air pressure. Their primary air user was the palletizing equipment. Second place was the dryer purge and a few leaks. And this cost a little under $12,000 a year to buy the electricity to run this compressor. They essentially had to spend no money. What they did was they got the compressor into the automatic mode, and they hung a big sign there, and they talked to everyone. They say, hey, we're going to run this in auto now, not hand. And the next time the technician came out to service the compressor, they had him adjust the load and the unload pressure settings to match the plant needs. All they really needed was 90 pounds of air. And so simply getting the compressor into auto, getting the mode changed, saved them $3,300 a year. It's not bad for a project that doesn't take any money. So let's compare load-unload control to inlet modulation. When a screw compressor unloads, the inlet valve closes or nearly closes, and a sump blowdown valve opens, and it blows the sump down, and it relieves the pressure in the sump. And the sump pressure determines the compressor power. If the sump blows completely down to atmospheric pressure, you can end up at near 18 or 20% power. But many compressors won't let the sump blow all the way down. They don't quite close that inlet valve all the way. They might hold 20 to 50 psi in the oil separator and they use that pressure to push oil, circulate oil through the compressor. And these compressors might have 30% power when unloaded, or 40%, or maybe even as high as 50% power. Case 1 shows a really good example of load-unload operation, where this system probably has lots of tank volume, and the compressor blows the sump down all the way, and so it has low unloaded power. Case 2 is kind of a bad example of load-unload operation, where they probably don't have much tank volume, and you can see that this compressor, even when it's unloaded, it's still consuming 50% power. So thinking back to our little palletizing compressed air system, what techniques are in play that these folks use to reduce their energy use? Let's see, this was the no-cost upgrade, where they went from modulation to load-unload control, and they adjusted the settings. Yep, so optimized pressure settings. Yeah, and 10, I make the most of your controls, right. They already had those. They just weren't using them. Excellent. Now let's move to another case study. This is a textile processing plant with a 225 horse variable speed oil flooded screw compressor. This compressor runs by itself. They have a second compressor, but it almost never operates. This compressor kind of runs from 40 to 100% capacity. It's discharging at 110 pounds. That's the set point. They have a nice cycling refrigerated dryer. And they also have a flow controller. We'll talk a little bit more about them. A flow controller is basically a fancy pressure regulator, and it's maintaining 90 psi downstream of the flow controller. They have lots of air storage, plenty of tanks everywhere. Their air users are primarily the textile processing equipment, which is not particularly pressure sensitive, 85, 95 pounds, everybody's happy. They also have many, many leaks, and during breaks, you could walk across the production floor and just hear the place hissing. These leaks were easy to find just with your ears, and they're using these barbed hose fittings. These barbed tubing fittings like this are notorious for having high leak rates, and this system was costing $86,000 a year to buy the power. Now you can see in our variable speed part load performance is pretty good, so that our percent power is pretty close to our percent airflow. So for example here, 40% capacity, we're using, a little bit more than 40% power. So that's pretty good. So power, it follows airflow pretty well. The upgrades this plant went after were they identified some of these problem areas that had these bad leaking tubing fittings, and they changed to a double ferrule type tubing fitting. And these have much lower initial leak rates and much lower long-term leak rates as well. And so by getting some wholesale upgrades to this different type of fitting, they killed a bunch of leaks in their plant. They also decided to bypass the flow controller and to just set the compressor discharge to 94 pounds. Now, flow controllers can be good when they're applied correctly, but they don't save energy in all cases. And in this case, it was causing them to run about a 16-pound higher discharge pressure with no noticeable benefit. And this project netted them a savings of about $22,000 per year, so sizable reduction. So back to our friendly concept list, go ahead and check the concepts that were used by the textile processor. Yeah, minimize loads for sure, killing those leaks, and the optimized pressure settings. Yep, they already had great controls. Their equipment was the right size. So yeah, getting the load down and getting the pressure settings down, $22,000 a year. Right on. Now let's go to a big system. We're actually not going to talk about the system as much as we are the air users. The supply side of this system totaled about 4,000 horsepower, was efficient, and it had very good controls, which is great. So if we were able to reduce air use, we reduce power use. Now, a partial list of their air users, they had 5 air-powered vibrators that were consuming 50 CFM. They had a handful of packaging and palletizing lines that were using compressed air to generate vacuum to lift cartons and containers. And these were consuming 284 CFM. And they had 9 vortex cabinet coolers that were consuming 117 CFM. Now, vortex cabinet coolers, if you haven't seen these, you put compressed air in, hot air comes out the top, and cold air comes out the bottom. They can become fouled, and the cold side won't get as cold as it should. And these are usually used to cool electrical cabinets, and they usually come with a thermostat these days. But some older units weren't supplied with thermostats and are just constantly in cooling. And then, like most systems, they have some leaks. A few leaks everywhere, but they had some sizable leaks inside their packaging equipment. So this plant went after the following upgrades. They replaced these air vibrators with electric units, which just simply use 10% of the power that the air units were using. They upgraded the vacuum generators, put in new vacuum generators on the packaging and palletizing lines. These generators shut off the air, not the vacuum, and they have an auto shut off at 20 inches of vacuum. They cleaned and repaired the vortex coolers and added thermostats where they weren't present. And they considered going in and doing some somewhat difficult leak repair inside some of these packaging lines, but there were thousands of tubing connections in there. And they decided that as a first measure, they were just going to install some automatic isolation valves on the packaging lines so that when the line went down, the compressed air was shut off, and that kind of killed all the leaks, at least when the line was down. So this totaled them 373 CFM of average flow reduction. And because they had good compressor controls, the flow reduction translated to dollar reduction. So this netted them $28,000 a year savings on a $31,000 project cost. So pretty good economics, about a 1-year payback. One more time, let's mark this up. Which concepts did these folks use? Yeah, minimize loads, and part of that was using the right technology. And let's see, was there another one? That's most of them. Getting the air use down and getting away from those pneumatic vibrators and getting the better vacuum generators. Yeah, I think that does it. Now let's talk about an auto parts manufacturer. These folks are operating 3 500 horsepower centrifugal compressors. 2 run during the week. One's base loaded and the other one's typically blowing off. And 1 compressor operates alone on the weekends, blowing off all weekend. They had some nice heated desiccant dryers with active purge controls, so not using very much energy there. And here's kind of a partial list of their air users. They have 8 bag houses that were consuming 175 CFM. They're constantly pulsing, constantly cleaning the bags. And they had another particular air user was a pressure-sensitive user that was a long way from the main header, fed by a very long 1-inch pipe. And there was a large pressure drop through this pipe, and it was forcing them to discharge at 115 pounds to keep this user happy. This cost them about $378,000 a year to operate this system. A little about centrifugals. Screw compressors and reciprocating compressors are positive displacement units, but centrifugal compressors are kind of like a common water pump. They use a high-speed impeller to pressurize the air. And centrifugal compressors really come into their prime around 400 horsepower and above. They cost less than screw compressors up in that size. They have good full load performance. They can potentially have lower maintenance costs, and they just naturally make oil-free air. The big drawback with centrifugals is their part load performance. They can turn down efficiently, but only at the top end of their range. This can be done using an inlet butterfly valve. You can see slightly different performance here. The inlet butterfly valve uses a little more power than inlet guide vanes do, but they have reasonably good efficiency in the top part of their range. Now, if we need less air than 70 or 80% air, they have to open up a blow-off valve and throw away the compressed air that isn't needed. If they were to continue closing the inlet valve, inlet guide vane or butterfly valve, the compressor would surge, which is very damaging to the compressor. So they're kind of stuck with this minimum flow that the compressor needs to make. So a centrifugal compressor uses roughly 75% power, anywhere from 0% capacity all the way to roughly 75% capacity. So this is bad news for operating at medium and low load for centrifugal compressors. What about this point down here? So similar to a screw compressor, a centrifugal compressor can operate at low power with the inlet valve shut and the blow-off valve open. But centrifugal compressors aren't commonly operated in load-unload type operation. It's more common to just see them just blow off the excess compressed air. Supply upgrades. So they went through and they upgraded all the compressor control panels, and on top of that they installed a supervisory control system to manage the compressors. This system's main benefit is that it modulates all the compressors simultaneously, and periodically it tests to see if it can shut down a compressor. On the demand side, they added differential pressure controls to the bag houses to stop them from cleaning the bags when it's not needed. These DP controls simply look at the pressure drop across the bag house filters and stop cleaning them at a low DP set point. And then when a high DP set point is hit, it starts cleaning the bags again. They're fairly simple controls, and they can save a lot of compressed air. This was about 110 CFM on average. They also installed a 2-inch line in parallel with that existing undersized 1-inch line, and so that just eliminated that pressure-sensitive user from being an issue at all. And that allowed them to drop their compressed air pressure down to 102 pounds. And this reduces artificial demand. And artificial demand is excess air used by leaks and unregulated users when you run at a higher pressure than necessary. Leaks always work better at higher pressure, so let's not give them that advantage. Now, this saved them $74,000 a year, but you can see it was a fairly expensive project cost, $178,000. The utility participated in this project and paid a good fraction of the upgrade cost to make it more attractive. Now, the controller the control upgrade, put that master controller in charge of all the compressors to try and keep them in their efficient trim range as much as possible. Try and keep them up here. It's better to have 2 compressors at 80%. Let's say if I had 2 compressors around here, about 80% capacity and 80% power. That would use less power than their old way of operation, which would have, 1 compressor at 100% capacity, and then the other compressor, down here, blowing off air and, consuming 75% power. The other neat thing about these control systems is that they're smart enough to test and see if they can shut off a compressor. So I believe it's 10 minutes, it will load the compressors up and try and unload the last compressor. And if the pressure, if it can unload that compressor and keep the system pressure steady for a certain amount of time, then it will shut off that last compressor. The control system also does other things like rotate through the compressors to prevent too frequent motor starts and even out run time and things like that. So our auto part maker used a handful of concepts, and let's mark up this list. Yeah, use your best part load option. I like that one. And most times we don't want 2 compressors to modulate to trim simultaneously. We just want 1. But in the centrifugal world, we actually do want that. So I like use your best part load option. Minimize pressure drops for sure, the 2-inch pipe. Turn it off. Yeah, the controls get that last compressor off. And minimize loads. Yep, getting the baghouse controls, the DP controls going there. All those. Remove barriers to more efficient. Yeah, that 2-inch pipe, it was a barrier for sure. Well, very good. Compressed air, as you probably know, is a very big world with lots of complexity. And thankfully, there are some good routes for assistance. And now we'll hear from Kelson from the Energy Trust.
Hi, can everybody hear me all right? My name is Kelson Redding. I'm with Energy Trust of Oregon, as was introduced, and I'm with the Production Efficiency Program. We help industrial and agricultural customers through the Energy Trust to get incentive funding for efficiency projects. So our job is to help everybody identify opportunities to save energy at your business, and also to help take advantage of the Energy Trust technical services and cash incentives when making upgrades or installing equipment that's going to save energy and essentially try to reduce costs for energy at your facility. So for industrial customers, your company gets served through Energy Trust by one of 3 program delivery contractors who deploy the Energy Trust Production Efficiency Program to the regional businesses. So which one of these program delivery contractors that serves your business depends on your business's location. You can reach out to Energy Trust to get aligned with the appropriate program delivery contractor to serve you. So we're by we, I should say, the program delivery contractors are industrial energy engineers whose purpose is to work with your business to help identify and to make the most of energy savings opportunities. So we've covered quite a bit of the typical air compressor energy saving opportunities that we see. We touched on the air compressors being used as efficient heat generation devices. One measure that I haven't seen in the examples is heat recovery, so that's another one that we have seen a lot with Energy Trust. So Any of the high-efficiency air compressors, switching from inlet modulation to load-unload, air compressor staging and sequencing, pressure reduction, VFD compressors, we can help with identifying the opportunity as well as the energy savings potential. And then on the backside of that, we can help get funding for good energy projects. So if you're planning to build a new facility, we also have technical services and incentives for that as well. Thank you for your interest. If you have any questions, we'll be addressing them at the end of the webinar. I'm going to turn it back over to Steve.
Thank you, Kelson. So the take-home message is compressed air is super versatile and it's used all over industry, but it's fundamentally inefficient. So let's use it carefully and make it efficiently. And with that, I'll hand it back to Beth.
Thank you, Steve. And I wanted to let folks know, remind folks that PGE and Energy Trust provide free energy efficiency consultations, and these can occur over the phone or in person. And if you're interested in finding out more, please contact Paula Conway at the phone numbers you see below, and she'll get you in contact with the correct PDC that Kelson mentioned. So before we proceed to the question and answer portion of the webinar, I wanted to remind you that you can continue to submit questions to me through chat. And I'll get the first question going here. It looks like, sorry. Steve, first question is, every time a compressor starts, I get a demand charge. Shouldn't I just leave them on then?
No, don't leave them on. That's a good question. We get that one a lot. Peak demand is charged based on your highest 15-minute energy use. And when you start a compressor, it does use a lot of power for a few seconds to get it moving. But if you look at that kind of high initial power usage over a 15-minute period, it really kind of disappears. It gets lost because it's just, 3 or 4 seconds out of 15 minutes. So it's better to shut that compressor off and let it come back on 10, 20, 30 minutes later, come back on whenever it's needed, than to leave it running.
Great. Next question is, how much tank volume is needed for load-unload control? A
standard rule of thumb is 5 gallons per trim compressor CFM. So let's say you have a 100-horse compressor that's making 500 CFM, and it's your only compressor. So you just take 500 CFM times 5 gallons, which give you about a 2,500-gallon tank. Now, if you have several compressors that might all be in the trim position, you would pick the largest compressor that might be trimming. So let's say that's a 1,000 CFM compressor. You can multiply that by 5, and so you'd end up with 5,000 gallons. That's a general rule of thumb, and it's pretty useful. I would say that's a good starting point.
Thanks, Steve. The next question is, how do I tell how much air my compressors are making?
Oh, that can be tough. If you have a system that's using load-unload control and isn't doing any modulation, you can kind of just get out a pad of paper and kind of time the load and the unload cycles. So if you time, let's say, 4 cycles, and it's totaling 2 minutes loaded out of 4 total minutes, then you know that that compressor is averaging 50% capacity. If you have a variable speed compressor, you're in a little easier situation where you can just kind of look at the compressor speed, or sometimes they'll display percent capacity, and that'll give you a feel for where you are. Centrifugal compressors can be quite hard to tell how much air they're making because they will tell you what the inlet valve position is and what the blow-off valve position is, but translating that into like airflow is pretty unreliable. So if you're a big enough system to have centrifugal compressors, you probably want to buy flow meters to help you understand your your air use. And if you have a modulating air compressor, that's similarly kind of tough because it's not like it makes a different sound, or there's no clear indication of how much air the compressors are making. Well, with one exception, Rogers Machinery and the Quincy compressors do have an inlet. They're using an inlet pressure to kind of give you an indication of capacity there, but most of the other manufacturers don't do that, and so you can't see compressor capacity. With a reciprocating compressor, the same thing. You could just kind of basically do a time study and just total up the number of minutes it was on, divide it by the total number of minutes that you were watching it, and that would tell you the capacity at that during your little study.
Okay. Kelson wanted to remind folks that Energy Trust can help identify compressed air opportunities in the facilities also.
Yeah. The other thing Kelson brought up was heat recovery. So, this 85% of our power that gets turned into heat and thrown away might not have to be thrown away. If there's, as Kelson mentioned, there's sometimes an opportunity to use that heat to preheat boiler water or to heat a shop, other things like that.
Great, thanks. I think we have time for one last question. And the next one that I have is, could I use both the refrigerated dryer and a desiccant dryer?
People generally don't do that, with the following exception. If you have a big system and let's say most of the air is used inside the plant, but you have some bag houses or some control valves that are up on the roof that you need to protect those lines from freezing, sometimes people will put in a master refrigerated dryer that's handling 95% of the air use, and then they'll put a small desiccant dryer for the air that's going outside the building so they don't have freezing problems in the winter. That's the one way that they're commonly combined. Another potential way to combine them would be if you had both, and you could run the refrigerated dryer during moderate and warm weather, and then during freezing weather you could run the desiccant dryer. But that's not super common. You only see that occasionally because now you have two pieces of equipment, and if someone doesn't forget to change it over, then you could potentially have problems. But running them back to back is generally not done, like through a refrigerated dryer, then immediately into a desiccant dryer. That's typically not done. I think it can actually cause some issues with the functioning of the desiccant dryer, because the airstream does, despite the attempt to reheat the air coming out of the refrigerated dryer, it is going to come out colder than it was before the dryer, and sometimes sending that cold air into the desiccant dryer can kind of hurt its ability to regenerate, oddly enough.
Okay. I want to thank you for that answer, and thank you all for joining us today. That was our last question.